As you unwind in the peaceful comforts of your evening tonight, I would like to take you on a voyage through space and time to discover one of Earth's most unseen but essential protectors. It's something you can't see, touch, or think about very often, but without it, the history of our planet, and possibly your own life, would have taken radically different turns. I'd love to know if you're enjoying this trip through the potential past of our alternate Earth. Please let us know where you're tuning in from and what time it is for you. Are you imagining these subterranean worlds from the safety of your own atmosphere? Or maybe from a location where you can see the stars that the people on our alternate Earth would never be able to see? If you will, picture yourself going outside on a clear night and gazing up at the stars. The crisp promise of changing seasons or the aroma of evening flowers is carried by the soft breeze as it brushes against your face. It's a delicate dance between our planet and the forces around us, the product of billions of years of cosmic choreography. However, something else is at work, something strong but unseen that envelops our world like a mystical hug. We're going to investigate what our world might have looked like if this silent guardian had never been created. This is Earth's magnetic field. Every facet of life, as we know it, is touched by this tale, which starts deep within the molten core of our planet and extends all the way to the very edge of space. We must first comprehend what we have in order to comprehend what we may have lost. Imagine Earth as a dynamic, living system, rather than the solid, immobile sphere we typically think of. The outer core of our planet, a churning sea of liquid iron and nickel heated to temperatures comparable to the sun's surface, is located nearly 3,000 kilometers below the surface of your feet. This is not the static, tranquil center you may have imagined from drawings as a child. Rather, it is a place of perpetual movement, where molten metal currents swirl and flow in patterns that would make the most intricate river system appear simple in comparison. These currents don't flow at random. They are propelled by the rotation of the planet, the heating and cooling of materials, and the same forces that propel our planet through space. Something amazing occurs as this liquid metal moves. Magnetic fields follow electric currents where they start to flow. It's the same idea that powers a basic electromagnet on a planetary scale. This process, which scientists refer to as the geodynamo, has been generating the magnetic cocoon that envelops our planet for billions of years. This process has incredibly beautiful mechanics. The liquid iron in the outer core is convecting, meaning that cooler material sinks and hotter material rises from deeper levels. Earth's rotation complicates this convection, causing what physicists refer to as the Coriolis effect. Together, these forces produce spiraling currents that, like cosmic taffy being drawn and molded by unseen hands, stretch and twist the magnetic field lines. However, what if it hadn't? What if things had turned out differently in the early stages of Earth's formation? It's possible that the planet's composition was different when it formed, lacking the iron-rich core required to generate magnetic fields. Perhaps the delicate balance required for the geodynamo to establish itself had been upset by our early collision with the Mars-sized body that most likely formed our moon, which knocked our planet's rotation into a different pattern. The planet may have cooled too slowly or too quickly, obstructing the precise temperature gradients required for convection. Though there are many options, the outcome would have been the same: a world devoid of its magnetic shield. Let's take a trip back in time to the early days of our planet's history, billions of years ago. As the young world revolves through space, it receives the same warming light from our star, forms the same early atmosphere through volcanic outgassing, and goes through the same gradual cooling and material differentiation processes. However, something essential is absent. This alternate world is still vulnerable to the harsh realities of space, whereas our Earth has developed its protective magnetic envelope. A fictitious observer would not have noticed the difference right away. The planet would have resembled our own in those early eons, before life had taken root. The gases that would make up the first atmosphere methane, ammonia, water vapor, and carbon dioxide would have been ejected from volcanoes that dot the landscape. The first oceans would have formed as a result of comets and asteroids bringing more water and organic materials. The primordial soup of possibility would have contained the essential components of life. However, there has always been a more violent side to our sun, that ostensibly kind source of warmth and light. The solar wind, a river of charged particles travelling at amazing speeds, is constantly streaming away from our star. These particles travel through space at speeds of up to 1,000,000 miles per hour. They are primarily protons and electrons that have been stripped from hydrogen atoms in the sun's corona. The solar wind is not consistent. It flows outward from our star like an unseen hurricane in streams and gusts, becoming weaker during quieter times and stronger during solar activity. Something lovely and protective occurs on Earth when these particles come into contact with our magnetic field. They are diverted, steered innocuously around our planet like water around a rock in a stream, or directed toward the polar regions, where they combine with our atmosphere to produce the auroras, which are dancing lights. The magnetosphere, a huge protective bubble that stretches tens of thousands of kilometers into space and far beyond our atmosphere, is created by the magnetic field. There would be no such defense or soft rerouting of these cosmic bullets on a world devoid of magnetism. Rather, the solar wind would directly impact the planet's atmosphere, atom by atom and molecule by molecule. Unlike wind blowing across a field, this is not a gentle process. High-energy particles have the power to literally disintegrate atmospheric gases or provide enough energy to launch them completely into space when they collide with them. This process, known as atmospheric stripping, would have persisted for billions of years, day in and day out. You may be wondering just how important this process is. After all, our atmosphere appears to be so large and substantial. You are taking in air from an ocean hundreds of kilometers above your head that contains about 5 quadrillion tons of gas. A few escaping molecules shouldn't be a big deal, right? However, when measured across geological epochs, the gradual becomes catastrophic, and time has a way of making the impossible seem inevitable. In contrast to Earth's thick layer of air, Mars, our neighbour, only has a thin layer of atmosphere today. According to available data, Mars' atmosphere used to be considerably thicker, possibly thick enough to sustain liquid water on its surface for extended periods of time. Water once flowed freely across the red planet's surface, according to ancient riverbeds etched into Martian rock. However, early in its history, Mars lost the majority of its magnetic field, most likely as a result of its smaller size and faster cooling, which stopped the convection processes in its core. The solar wind gradually but surely eroded most of Mars's atmospheric shield over geological time, possibly hundreds of millions or even billions of years. Any human visitor would require a pressure suit to prevent their blood from literally boiling in the low-pressure environment, as what is left today is less than 1% as thick as Earth's atmosphere, so thin that liquid water cannot exist on the surface under normal circumstances. The story would have been even more dramatic if our hypothetical Earth had taken a similar course. Because Earth is nearer the Sun than Mars, the solar wind is more powerful and persistent here. There are more particles per unit area, and they arrive with more energy. In the absence of magnetic shielding, the atmosphere of our planet would have been subjected to a more severe and prolonged attack than Mars has ever encountered. The process would have taken hundreds of millions, if not billions of years to develop. However, the atmospheric layer covering our planet would have gotten thinner and thinner over time, unavoidably. Only the heaviest molecules, and those that could somehow find refuge in the planet's gravitational well, would have remained after the thicker portions of the atmosphere were removed first. Even these may eventually have been destroyed by the unrelenting sunbeams. Let us now take a moment to reflect on the implications of this for the possibility of life. You're experiencing conditions that rely solely on the existence and density of our atmosphere. If you're reading this from a cozy spot tonight, maybe with a hot cup of tea close by or the gentle sound of rain hitting your windows, the reason for the comfortable temperature you're experiencing is that our atmosphere retains heat from the sun, avoiding the drastic temperature fluctuations that would happen in a world without air. For billions of years, photosynthetic life, organisms that could only flourish because our atmosphere offered the stable conditions they required, produced the breathable oxygen in the air you're breathing right now. Enough atmosphere is necessary to trap heat, move air masses, and establish the stable conditions necessary for life. This includes the protective barrier against the vacuum of space and the moisture distribution that produces weather patterns and allows rain. Without enough atmosphere, our alternate Earth would have changed drastically, possibly taking on the characteristics of a hybrid of our own Moon and Mars. There would have been abrupt and severe temperature changes. The day side might have gotten extremely hot, and the night side might have gotten extremely cold if there hadn't been air to disperse heat around the planet. Without wind patterns distributing temperature and humidity across continents, clouds collecting moisture from the oceans and transporting it inland, and the protective ozone layer filtering harmful radiation from space, weather, as we know it today, would not have existed. It is possible that the idea of seasons, those soft rhythms that signal the passing of time and serve as the setting for so much of the drama in life, would never have come into being. Only the harsh contrast between the furnace of day and the freezer of night would exist, tempered only by the thin wisps of atmosphere that might occasionally gather in the deepest valleys or craters, rather than the slow warming of spring or the crisp promise of autumn. This is where, however, our story takes its first intriguing turn. Life is incredibly resilient and inventive, as we have repeatedly found in the most unexpected locations on our own planet. Life may still have found a way to start on this magnetically barren Earth. The conditions under which the earliest life forms on our planet evolved would be fatal to the majority of living things today. In the crushing depths of the ocean, where no sunlight ever reaches, in environments with little to no oxygen, in scorching hot springs that would instantly kill modern organisms, in conditions so harsh that we refer to the creatures that inhabit them as extremophiles, lovers of the extreme. These early life formers didn't require the cozy surroundings that sophisticated life demands. They were straightforward, resilient, and highly adaptive. Others consumed the chemical energy emitted by volcanic eruptions. The radiation that would kill more complex organisms was a source of life for others. Many could endure extremes in salinity, acidity, temperature, or pressure that would denature the proteins of more complex organisms. On our alternate Earth, life might have sought refuge underground, where atmosphere and pressure could still be sustained. Imagine extensive underground networks of caverns and caves that have been sculpted over millions of years by volcanic and water processes. Here, pockets of atmosphere could be trapped and shielded from the relentless stripping of the solar wind. Kilometers below the hostile surface, geothermal energy from the planet's core could supply warmth and chemical energy for life processes, while the rock above would act as a shield against cosmic radiation. By our standards, these subterranean ecosystems would have been completely alien. They could not have evolved photosynthesis as we know it if they had no access to sunlight. Rather, they may have developed around chemosynthesis, which uses chemical reactions involving gases and minerals that leak from the planet's interior to produce energy. Consider the creatures that live near deep-sea volcanic vents today. These creatures have never seen sunlight and have based their entire ecosystem on the chemistry of dissolved minerals and heated water, bacteria that break down hydrogen sulfide, organisms that flourish in water hot enough to melt lead, and tube worms that grow meters long without ever consuming anything we would consider food. Such societies may have made up the entire population of our alternate Earth, surviving in the shadows and flourishing in the depths, forming a secret biosphere that stretched around the world via interconnected networks of caverns and subterranean waterways. Over the billions of years that these communities had at their disposal, they may have expanded to enormous size and complexity, creating complex food webs that relied solely on the cycling of minerals and chemical energy. Imagine, if you will, enormous subterranean lakes that are warmed by geothermal springs and have mats of vibrant bacteria growing along their shores, producing planetary abstract art. Living organisms may have created the mineral formations that line cavern walls, obfuscating the distinction between geology and biology. It's possible that strange chemical processes generate their own bioluminescence, giving the subterranean landscape an unearthly glow that has no names in our language. The bubble and gurgle of geothermal springs, the faint chemical hiss of mineral precipitation, and the distant sounds of vast microbial communities going about their ancient business are just a few of the sounds that may reverberate from these underground realms. The world would be more subdued and quieter than ours, but it would still be vibrant despite its differences. However, this begs the intriguing question: was it ever possible for complex life to arise from such lowly origins? The invention of photosynthesis marked a significant turning point on our planet. About 3 billion years ago, cyanobacteria discovered how to use sunlight to feed themselves. They also started releasing oxygen into the atmosphere, which drastically altered the chemistry of our planet and allowed for the emergence of more complex oxygen-breathing life. Since oxygen was poisonous to the anaerobic organisms that dominated early Earth, this event, sometimes referred to as the Great Oxidation Event, was actually disastrous for the majority of life forms at the time. But compared to their anaerobic cousins, organisms that were able to adjust to the new oxygen-rich environment had access to a lot more energy. The energy budget required for complex, multicellular life is provided by oxygen-based metabolism, which is about 15 times more efficient than anaerobic processes. This photosynthetic revolution would never have happened, at least not globally, on a planet without a surface atmosphere. It's possible that tiny communities of life close to subterranean water sources have evolved strategies for making use of the scant light that seeps through crevices and cracks. However, it would not have been possible for the enormous, revolutionary explosion of oxygen production that changed our planet. This implies that our alternate world would have lasted far longer than the billion years or so it took for our planet to form, probably remaining in a state similar to Earth's earliest biological era, which was dominated by simple microorganisms. Multicellular life, complex cells with nuclei, and the explosion of diversity found in the fossil record on Earth could have all been forever postponed or never occurred. However, there is a certain beauty in envisioning these subterranean worlds evolving into complex entities of their own. Evolution might have followed more patient, subtle paths if photosynthesis hadn't given our planet its energy windfall. Even though they didn't resemble our familiar plants and animals, these microbial communities may have evolved forms of organization and cooperation over billions of years that we would consider complex. Imagine underground networks of microbial colonies that cover entire continents and communicate via chemical signals that pass through rock formations and groundwater. It's possible that these planetary organisms have evolved memory and learning systems, storing environmental information in the patterns of their chemical networks. By relocating resources and population centers in response to minute variations in temperature, pressure, and chemical composition that signal earthquakes or volcanic eruptions, they may have developed the capacity to anticipate and prepare for geological events. Let's now go back in time to our alternate Earth and investigate what might have transpired as the planet continued to undergo geological reshaping. More than just atmospheric retention and the emergence of life would have been impacted by the loss of our magnetic field. The relationship between our planet and space itself would have been drastically changed, with ripple effects that would have affected everything from the surface geology to the planet's rotation. The upper atmosphere and surface of our planet would have been continuously bombarded by charged particles from the solar wind if there had been no magnetosphere to deflect them. It wouldn't have been a gentle bombardment because these particles are very energetic and can alter the chemical and physical composition of surface materials or molecules in the atmosphere. This bombardment may have gradually changed the planet's spin over geological time. The motion of objects in space can be affected by the solar wind's subtle but enduring force, which physicists refer to as radiation pressure. This force is mostly repelled on a planet shielded by a magnetic field. However, on our alternate Earth, the solar wind's constant pressure may have served as a cosmic brake, slowing the planet's rotation over billions of years. At first, this effect would have been extremely subtle, possibly slowing down each day by a few microseconds annually. However, these small changes would have added up over the long periods of geological time. It's possible that our alternate Earth's days were significantly longer than ours, and that it rotated so slowly that by our standards, the cycles of day and night lasted weeks or months. It's possible that the planet eventually became tidally locked to the Sun, displaying the same face to our star in the same way that our moon does to Earth. A world with perpetual day on one side and perpetual night on the other, with only a small twilight zone in between, where conditions might still be mild enough for life to survive, would result from this. Without night to provide cooling relief, the day side of such a world would have turned into a furnace, baked by the sun's unrelenting rays. It's possible that surface temperatures reached hundreds of degrees, which would have melted metals and evaporated any water that remained. Any lingering atmosphere might have frozen solid and turned to snow on the night side, which would have been the opposite extreme, a place of unending cold. However, there may have been a small area where temperatures stayed moderate along the terminator, which is the line that separates day from night. This twilight zone, which may have been hundreds of kilometers wide, and where the last remnants of the atmosphere may have gathered, where liquid water may still exist, and where life may have made its last stand above ground, may have developed into the planet's most biologically active region. As this habitable zone gradually moved as a result of minute changes in the planet's rotation and orbit, picture the enormous migrations of organisms that followed. The terminator line would have strayed across the surface over millions of years as the planet's position was subtly altered by gravitational interactions with other planets, and life would have had to adjust to this cosmic nomadism. It's possible that these terminator ecosystems evolved amazing survival techniques. Maybe they would have developed the capacity to quickly hibernate or insist when the environment got too harsh, awaiting the return of the habitable zone. Perhaps they would have acquired extraordinary mobility, enabling them to move between continents by adhering to the limited range of temperate conditions. Utilizing the energy differential between hot and cold areas, some may have evolved the capacity to flourish in the harsh temperature gradients at the boundaries of the habitable zone. Our alternate Earth surface geology would also provide a very different picture. In addition to shielding the atmosphere, our planet's magnetic field influences the way cosmic radiation interacts with materials on the surface. In the absence of this defense, cosmic rays, high-energy particles from deep space that can pierce deep into solid matter, would have continuously bombarded our alternate world. This cosmic bombardment would have significantly altered the rocks and minerals on the surface over geological time. Cosmic rays have the power to change crystal structures, produce new isotopes, and initiate chemical reactions that would not normally take place. Our alternate Earth's rocks may have acquired distinct compositions and characteristics, including isotopic signatures, that reveal the effects of exposure to cosmic radiation over billions of years. It's possible that these radiation-modified minerals produced landscapes that are unlike anything found on our safe planet. They might have produced surfaces that shimmer and glow with internal light by forming crystals with peculiar optical characteristics. Perhaps complex organic molecules would have formed in rock formations due to the continuous radiation, resulting in a type of geological life that exists at the intersection of biology and chemistry. Meteoroids that would typically burn up in our atmosphere would reach the surface undamaged if there was no atmospheric shield. The accumulation of impact craters over billions of years would produce a landscape that resembles the Moon or Mars more than the Earth as we know it. However, our alternate Earth would still have been experiencing geological activity, such as earthquakes, volcanic eruptions, and the gradual drift of continents, in contrast to those worlds. It's possible that impact cratering and continuing geological processes combine to produce genuinely alien landscapes. Imagine enormous crater fields inside old impact basins where new mountains have been formed by volcanic eruptions. Imagine deep canyons filled with the odd radiation-altered minerals that tell the tale of cosmic bombardment, where the planet's crust has broken apart to form rift valleys. Since there wouldn't be any wind or rain to erode these craters away, they would stay pristine for a lot longer than they would on Earth. Every strike would leave a lasting mark on the terrain, a record of cosmic occurrences spanning billions of years. For short geological periods, surface life may have persisted in isolated pockets created by the largest craters, turning into deep basins where any leftover atmosphere could gather. However, the idea of life continuing on such a planet has a deeply poignant quality. Life would find a way to not only survive, but also to flourish and evolve in the face of overwhelming odds and in environments that appear to be hostile to everything we know about biology. It serves as a reminder that the creativity of life transcends our earthly experience and that there may be forms of existence in the universe that we have never imagined. Let's think about what might have happened if our planet, which lacks a magnetic field, had managed to hold on to enough atmosphere to sustain surface water, at least in some areas. The planet may have been able to retain more of its atmospheric blanket in spite of the solar wind's attack because of its larger size than Mars, a different atmospheric composition, or the shielding effect of a particularly strong greenhouse effect. We could envision a world of stark extremes and contrasts in this scenario. In the deepest basins, the surface may be dominated by huge shallow seas, shielded by whatever thin atmosphere was left. Due to billions of years of evaporation under intense solar radiation, these seas may be extremely saline. These waters' chemistry would be completely different from that of the oceans on Earth today, possibly full of dissolved minerals and other substances that complex ecosystems have never had a chance to process. Compared to the comparatively fresh waters of Earth's oceans, the salinity of these seas may be so high that they resemble liquid mineral deposits. However, life's extraordinary tenacity may have allowed it to flourish despite these extremely salinized conditions. Some living things on Earth already survive in extremely salinized environments, such as salt lakes, subterranean brine deposits, and the saltiest parts of our oceans. It's possible that life in these extraterrestrial waters took on nearly crystalline forms, creating complex structures out of the many minerals dissolved in the extremely salinized environment. These organisms have the potential to create enormous living reefs composed of both biological material and precipitated minerals, obfuscating the distinction between living tissue and geological formation. They may have developed the ability to manipulate mineral precipitation, creating structures and shells out of dissolved salts with such accuracy that human engineers would be envious. Such a world, with its surface painted in colours that have no corresponding hues in the earthly palette, might seem to sparkle and shine with an unearthly beauty from space. Unusual light reflection from the hypersaline seas could produce crystalline landscapes that shimmer. Large salt flats that stretch to the horizon, where these seas met the land, may have been covered in mineral deposits and resilient microorganisms that gave them their vivid hues. The continents may have been left as huge empty stages for purely geological dramas due to the absence of complex land life. Without animals to mix and disturb sediments and plants to break down rock and produce soil, the landscape may have stayed mostly the same for billions of years. It's possible that old mountain ranges remain intact, untouched by the erosion that shapes the surface of our planet. Canyon systems of amazing size and geometric accuracy could be formed by rivers, if there were any, cutting deep, straight channels through bedrock. Without the biological cycles that mold the surface of our planet, these geological processes would have continued to function. There wouldn't be a nitrogen cycle fueled by bacterial activity, an oxygen cycle sustained by photosynthesis, or a carbon cycle powered by living things. Rather, geological processes such as volcanic outgassing, mineral weathering, and chemical precipitation would be the only factors influencing the chemistry of our alternate Earth. This may have eventually produced chemical environments that are entirely different from what we're used to. Unusual chemical compounds that only form under particular temperature, pressure, and radiation exposure conditions might have taken over some areas. Forms of life that use completely different biochemistries from anything on Earth may exist in these chemical landscapes. These organisms may breathe sulfur compounds, metabolize metals, and construct their cellular structures from minerals rather than organic molecules. The quiet of our alternate Earth, however, might be its most poignant feature. The sounds of life are all around us. The rustle of leaves in the wind, the distant crash of waves formed by tidal forces influenced by marine ecosystems, the choruses of insects in the summer evenings, and the songs of birds that greet each dawn. We hardly ever notice these sounds because they are so ingrained in our daily lives, but they are the manifestation of billions of years of evolutionary creativity expressed through rhythm and vibration. In the absence of complex surface life, our alternate world might only be familiar with the sounds of geology, the crack of thermal expansion and contraction as surface materials heat and cool with the extremes of day and night, the whistle of thin wind across desolate landscapes, the crash and hiss of volcanic eruptions, and the rumble of earthquakes as tectonic plates shift and grind against one another. However, there may be sounds we have never heard before in the depths, in those safe underground worlds we previously envisioned. The faint vibrations of vast microbial communities going about their ancient business, the bubble and gurgle of geothermal springs, and the subtle chemical hiss of mineral precipitation. These would be the hints of an alternative existence, one that is just as real despite being outside of our experience. These subterranean ecosystems may have evolved their own acoustic communication systems. Imagine a planetary nervous system that spans continents with microbial communities communicating via chemical signals transported by subterranean water systems. A sort of geological music that narrates the persistence of life in the deep may be produced by the patterns of these chemical communications. Our alternate Earth's interaction with cosmic forces may have produced intriguing effects as it grew older, and its relationship with space continued to change. Without a shielding magnetic field, cosmic radiation and the solar wind could have interacted directly with the planet's surface and any lingering atmosphere, changing the planet's physical characteristics over time. These interactions may have led to complex changes in the planet's rotation over geological time. In addition to providing a basic braking effect, the solar wind's intensity fluctuates with cycles of solar activity, producing recurring forces that may cause the planet to wobble or alter its axial tilt. On our stable, magnetically shielded planet, these changes may have produced intricate climate patterns unmatched by anything else. Imagine a world in which the distribution of solar energy across the surface undergoes drastic changes due to significant shifts in the axis angle over millions of years. Once moderate regions could turn into extreme ones, and once uninhabitable areas could momentarily turn into oases of mild weather. If life continued on such a world, it would have to be extraordinarily adaptive in order to endure both the gradual changes that take place over geological time, as well as the sudden environmental extremes. It is possible that these axial variations gave rise to what we might refer to as geological seasons, million-year intervals during which the world's conditions gradually changed from one extreme to the other. There may be brief periods during which ice may form at the poles, and moderate conditions may spread farther from the equatorial regions due to the planet's tilt during some epochs, which causes more solar energy to reach the polar regions. The planet may tilt more sharply in other eras, focusing solar energy at the equator and intensifying the polar regions. It's possible that organisms that have adapted to such a world have developed amazing survival mechanisms for these geological seasons. It is possible that some species have evolved incredibly long lifespans, surviving several axial shifts. Others may have developed the capacity to go into suspended animation for millions of years in order to wait for the right circumstances to reappear. As climate zones gradually change due to the shifting axial tilt, still others may have developed extraordinary mobility and migrated across continents. It's possible that special atmospheric chemistry was produced by the interaction of cosmic radiation with any residual atmospheric gases. High-energy particles would continuously interact with atmospheric molecules in the absence of a strong magnetic field, causing chemical reactions that wouldn't normally take place. Unusual compounds that are absent from Earth's protected atmosphere may have been produced by these reactions. Life may have benefited from some of these radiation-induced chemical reactions. They might have produced intricate organic compounds that organisms with the necessary adaptations could use as nutrients. Perhaps the steady stream of cosmic radiation would have pushed atmospheric chemistry in ways that would have made the environment more conducive to some forms of life. But let's put these hypothetical situations aside and think about what would have happened to one important part of the history of our planet. The evolution of consciousness and intelligence had Earth's magnetic field not existed. In addition to billions of years of evolution, exceptionally stable conditions over extended periods of time were necessary for the transition from simple microorganisms to sophisticated, thinking beings. Consistent environmental conditions that permitted the slow accumulation of biological complexity were necessary for the development of sophisticated nervous systems and brains with consciousness, reasoning, and self-awareness. From basic reaction mechanisms to sophisticated sensory systems to abstract reasoning, every stage of the development of intelligence built on the one before it in a convoluted chain of ever-increasing complexity. With its thin atmosphere, high radiation levels, sharp temperature fluctuations, and ever-changing environment, our alternate Earth may never have offered the stable environment required for this type of slow evolutionary development. Instead of permitting the type of experimental complexity that ultimately resulted in consciousness on our planet, the ongoing environmental stress may have kept evolution concentrated on basic survival. Complex brains require a tremendous amount of energy. Even though they only make up around 2% of our body weight, human brains use 20% of our metabolic energy. Only in an environment where organisms can consistently obtain enough nutrients and are not required to allocate all of their resources to immediate survival needs is this type of energy budget feasible. It's possible that the energy requirements for survival on our hostile alternate Earth were so great that evolution was never able to experiment with energy-intensive organs like sophisticated brains. Basic survival, protecting cellular structures from radiation damage, and adjusting to ever-changing circumstances would have required every calorie. The rarity of intelligence in the universe is called into serious question by this. Perhaps Earth-like intelligence is much less common than we might think if complex life and consciousness require stable, protective magnetic fields to develop. Simple life may exist throughout the universe, with planets supporting enormous ecosystems of microorganisms and possibly simple multicellular creatures. But the particular circumstances required for beings to be able to reflect on their own existence may be incredibly rare. Scientists use the Drake equation, which accounts for both the evolution of intelligence and the emergence of life, to calculate the probability of intelligent life in the universe. The likelihood that any planet could produce sentient beings would be greatly diminished if protective magnetic fields were a necessary condition for the emergence of intelligence. It's possible that the universe is much more isolated than hopeful estimates indicate. However, this story also offers cause for wonder and hope. It implies that biology is far more inventive and adaptive than we occasionally think if life could find ways to flourish in the hostile environment of our alternate Earth. Perhaps entirely different evolutionary pathways could give rise to intelligence, evolving in ways we haven't thought of. Eventually, the enormous microbial communities of the subterranean ecosystems of our alternate world may have developed networks of coordination and communication that span entire planets and are identifiable as conscious, even if they don't resemble our own individual minds. It is possible that these planetary intelligences perceive the world in ways that are entirely different from our own embodied consciousness. They may experience thoughts that develop over millions of years, thinking in geological time. The chemical structures of old rock formations, which act as a sort of mineral library, may contain forms of memory that date back to the early days of the planet. They may find beauty and significance in patterns of subterranean water flow that span continents, and they may dream in the language of mineral precipitation and thermal cycling. Our values and concerns may differ greatly from those of such intelligences. They may think in terms of planetary stability and chemical balance, whereas we think in terms of individual survival and reproduction. Where we produce music and art, they may produce intricate mineral deposition and chemical cycling patterns that convey aesthetic qualities we can hardly fathom. They could send messages through the planet's hydrological systems at speeds that would appear glacially slow to us but are entirely normal to creatures that measure time in geological epochs. They could do this by subtly altering the chemistry of the groundwater. Their discussions could go on for thousands of years, delving deeply and patiently into philosophical issues regarding the nature of existence that would be impossible for individual minds to accomplish. Through their planet's reactions to gravity, these planetary minds may have eventually developed an awareness of the universe outside of their own, picking up on the rhythms of celestial mechanics. They may have formed a science based on emotion and intuition rather than outside observation, gaining a profound understanding of physics and astronomy via first-hand experience of how cosmic forces impact their environments. It's important to consider what this thought experiment tells us about our own world and our place in the universe as we draw to a close our exploration of the potential history of this alternate Earth. Because it is so completely dependable, it is easy to take for granted the invisible, intangible magnetic field that envelops our planet. For billions of years, it has been keeping us safe by silently and continuously preserving the circumstances that allow us to exist. This invisible guardian is responsible for every breath you take while listening to this, every instance of stable weather you've ever had, and every sunset you've ever savoured. Because of the ability of our atmosphere to retain and disperse heat, your room is currently at a comfortable temperature. Our magnetic field kept the atmospheric conditions necessary for photosynthetic organisms to flourish for billions of years, which is how the oxygen in your air was created. We also have a very complex and dynamic magnetic field. It is a complicated, ever-evolving pattern of magnetic force lines that shift and change over time, rather than a straightforward dipole like a bar magnet. Over decades, the magnetic poles can shift hundreds of kilometers. Regional variations in field strength result in magnetic anomalies that impact everything from satellite operations to compass readings. At times, our magnetic field becomes much weaker, and very infrequently, maybe once every few 100,000 years, it reverses entirely, turning magnetic north into magnetic south and vice versa. Earth's protection is momentarily diminished, but never completely removed, during these reversal periods which can extend for thousands of years. Although the exact relationship is unclear, Fossil evidence indicates that some of these reversals have occurred during times when extinction rates have increased. Even though our planetary defense system has proven to be dependable, these natural variations serve as a reminder that it is not static or permanent. In order to comprehend the past of our planet and to get ready for any future changes, scientists closely examine these changes. Although magnetic field reversals usually take thousands of years to occur and do not immediately endanger life on Earth, there is some evidence that we may be in the early stages of one right now. Our magnetic field would only weaken and reorganize into a more complex pattern before finally settling into the reversed orientation, so even during a reversal, it wouldn't completely vanish. However, the fact that this system on which we rely so heavily is undergoing change and evolution over geological time is a sobering reminder. The interdependence of the planetary systems that enable our world to support life is another point of emphasis in the tale of our alternate Earth. Scientists are still trying to figure out how the magnetic field, atmosphere, oceans, climate, and life itself are all closely related. Everything else reacts and changes when you make a big change to one component. The intricate interactions between numerous systems, each of which supports and reinforces the others, are what make Earth habitable rather than any one element acting alone. This viewpoint is especially pertinent as we think about the future of our planet and our responsibility as its temporary stewards. Numerous systems on Earth are being altered by human activity, including the stability of the climate, the diversity of life, the chemistry of the oceans, and the atmosphere. Although the magnetic field is beyond our control, we do have some control over many of the other systems that keep our planet habitable. We can better appreciate the value and fragility of the conditions we enjoy when we consider how different these systems may have been. Beneficial feedback loops and lucky coincidences over billions of years have created our cozy, stable environment. It is a remarkable convergence of cosmic circumstances that we exist at all as conscious beings with the ability to think about these questions. Visible indicators of our magnetic field in action are the aurora borealis and aurora australis, those dancing curtains of light that adorn our polar skies. Photographs or videos of these ethereal displays show how the solar wind and the magnetic shield of our planet intersect. These lovely lights are produced by the same particles that would otherwise be destroying our atmosphere, but our magnetic field turns them into works of art that are painted across the sky. These auroras happen when particles from the solar wind collide with gases in the upper atmosphere's thin air, guided by our magnetic field lines. When these particles hit oxygen atoms, they release red and green light. Blue and purple colours are produced by nitrogen. The intricate, dynamic structure of our magnetic field, as it reacts to changes in the solar wind, is reflected in the forms and motions of auroral displays. The sky would not be so beautiful on our alternate Earth. Perhaps the harsh reality of unfiltered cosmic radiation reaching the surface will replace auroras. The faint glow of any residual atmosphere from continuous bombardment would be the glow of destruction rather than creation, the light of molecules being torn apart instead of momentarily energized and released. Nevertheless, we can draw inspiration from life's tenacity and inventiveness even when we imagine this more brutal world. Life finds ways to not only survive but also thrive in environments that would quickly kill more familiar organisms, as demonstrated by the extremophile organisms that flourish in Earth's most difficult environments, such as boiling hot springs, extremely acidic pools, the crushing depths of ocean trenches, and the radioactive zones surrounding nuclear reactors. The types of life that might arise on our alternate world could be modelled after these resilient pioneers of Earth's harsh environments. Certain bacteria can withstand radiation exposures thousands of times greater than those that would kill humans. Others flourish at temperatures high enough to cause metals to melt. Others inhabit chemical environments that are so corrosive that they would dissolve the majority of the materials we use on a daily basis. Imagine what kinds of life might develop in the genuinely harsh conditions of a world without magnetic protection if such organisms can survive in the comparatively mild, extreme environments of our protected Earth. By our standards, these organisms may develop biological processes that are almost magical, metabolisms that obtain energy from chemical processes we consider destructive, cellular structures that operate at temperatures that would vaporize organic molecules as we know them, and the capacity to repair radiation damage more quickly than it accumulates. These extreme organisms may have evolved into complex ecosystems unlike anything we have seen in our alternate Earth's billions of years of evolution, even without the abundance of energy that photosynthesis gives our planet. They might have evolved strategies of competition and cooperation that produce complex networks of interaction. All life on our alternate Earth would have continued to rely on chemical energy sources, such as the heat and chemical gradients produced by geological processes in the absence of photosynthesis. However, this does not imply that such a world would be any less complex than our own. It would simply be different. Rich, complex biological communities can exist completely without the presence of sunlight, as demonstrated by the ecosystems surrounding hydrothermal vents in the deep oceans of Earth. In addition to bacteria, these vent ecosystems are home to complex animals like fish species that are unique to Earth, giant tube worms, and unusual crabs. They establish their own food webs using only chemosynthesis, demonstrating that photosynthesis is not necessary for biological complexity. We might envision biological diversity on our alternate Earth that is comparable to or even greater than our own, but constructed on completely different foundations, given that it would take billions of years for such chemosynthetic ecosystems to evolve. In a world like that, the rocks themselves would record the geological past in ways that may be much more dramatic than those found on Earth. The interaction between the planet's interior and surface may have produced mineral formations and geological structures that tell tales of cosmic bombardment, atmospheric loss, and chemical extremes if there had been no life to buffer and moderate chemical processes. Imagine rock formations with layers that document cosmic ray bombardment over billions of years, with each stratum providing a different perspective on the planet's exposure to space. A geological record of our star's behavior over cosmic time could be created by the isotopic signatures found in these rocks, which might provide information about the history of solar activity. In ways that our own magnetically shielded planet cannot, such a world could be a goldmine for learning about the long-term evolution of our solar system. Our alternate Earth surface minerals may have characteristics that almost seem like science fiction. It's possible that constant exposure to high-energy particles produced crystal structures that aren't found on our safe planet. Unusual optical, electrical, or magnetic characteristics of these radiation-forged minerals may have impacted the evolution of any living forms that came into contact with them. It's possible that some life forms have evolved to use these special minerals in their biological structures, resulting in organisms with characteristics and materials not found in Earth biology. Consider organisms that construct their shells from radiation-altered minerals that offer defense against cosmic rays, or creatures with crystalline components that endow them with extraordinary abilities to sense electromagnetic fields. The carbon cycle on our alternate Earth would have functioned very differently from ours if there had been no complex surface life. Living things are essential to the movement of carbon between the atmosphere, oceans, and rocks on our planet. Carbon dioxide is drawn from the atmosphere by plants and incorporated into their biological structures. A portion of this carbon is buried in sediments after they pass away, eventually creating deposits of fossil fuels. Our alternate Earth's atmospheric carbon dioxide levels would be solely regulated by geological processes, such as volcanic outgassing and chemical weathering of rocks, in the absence of this biological carbon cycle. Over geological time, this could have resulted in drastically different atmospheric compositions, possibly alternating periods of cooling that caused atmospheric gases to freeze out and fall to the surface, with periods of greenhouse warming that help the planet retain more atmosphere. Geological epochs with drastically different conditions may have been produced by these long-term atmospheric cycles, possibly offering windows of opportunity when surface conditions improved and became more conducive to life. Liquid water may have been stable on a larger portion of the planet's surface during warm periods when a thicker atmosphere accumulated, enabling brief evolutionary radiations before the environment deteriorated once more. In contrast to the steady rise in complexity in our own world, such climatic cycles may have pushed evolution in quite different directions. Life on our alternate Earth may have undergone sporadic episodes of rapid evolution and adaptation, followed by protracted periods of dormancy or simple persistence, as opposed to gradual, continuous evolution. The planet's distinct atmospheric and magnetic history would also have had an impact on the relationship between our alternate Earth and its moon. By stabilizing Earth's axial tilt, the moon's tidal forces help avoid drastic fluctuations that could lead to disastrous climate shifts. However, the presence of oceans and atmosphere also contributes to the moon's tidal effects by generating the friction that progressively slows Earth's rotation and pushes the moon farther away. The moon's evolution might have gone differently on a planet with a weak atmosphere and possibly no stable surface oceans. It might have stayed nearer the Earth, producing more powerful tidal forces that could have contributed to the longer-term maintenance of some geological activity. Alternatively, the moon might have moved away faster in the absence of oceanic and atmospheric tides to generate friction, which would have lessened its stabilizing effect on the planet's rotation. The planet's long-term habitability may have been impacted by intricate feedback loops produced by these orbital dynamics. Variations in the moon's distance would have an impact on the planet's interior tidal heating, which would change volcanic activity and atmospheric component outgassing. In the meantime, variations in the planet's rate of rotation would have an impact on the distribution of the planet's remaining thin atmosphere, as well as the patterns of atmospheric circulation. I hope these explorations are stimulating your thoughts if you're still traveling with me through space. If you like these in-depth explorations of alternate universes and cosmic what-if scenarios, please consider subscribing. There is so much more to discover in the fields of science and creativity. We might envision a number of different outcomes for our alternate Earth story as we contemplate its long-term destiny. One possibility is that, like our moon, the planet may eventually lose so much of its atmosphere that it is airless. Any surviving life would be restricted to the deep underground, where geological processes could continue to sustain pockets of atmosphere. However, there is also a chance that the planet may eventually acquire a new type of stability. Maybe the remaining atmosphere would be so thin and made up of such heavy gases after billions of years of atmospheric loss that the rate of loss would drastically slow. When the rate of atmospheric loss equals the rate of outgassing from geological processes, the planet may achieve a new equilibrium. Perhaps made up primarily of noble gases like argon and xenon, which are less vulnerable to being removed by the solar wind, this equilibrium atmosphere could be very different from anything we are familiar with. An atmosphere like that might still be thick enough to support some life forms on the surface, but it would not produce much greenhouse warming and would be inhospitable to any of the known life forms. According to this scenario, our alternate Earth may eventually resemble a cross between Mars and Venus, too thin to sustain life on Earth, but thick enough to produce weather patterns and possibly sustain liquid water in some areas. The distinct chemistry of this exotic atmosphere may paint the surface with hues and formations that are unmatched in our solar system. Some of the most unusual life forms we can think of could develop in such a setting. The chemical reactions between surface minerals and atmospheric gases could provide them with energy. They may be able to endure conditions close to vacuum, perhaps spending a portion of their life cycles as airborne spores floating through the thin atmosphere, and another portion as organisms that live on the surface and are resistant to extreme temperatures and radiation. It's possible that these organisms have developed extraordinary senses and reactions to cosmic radiation, possibly utilizing it as a source of information as well as energy. They may be able to identify and decipher the minor changes in cosmic ray intensity brought on by solar cycles, seasonal shifts in Earth's orbit, and even the planet's journey through various galactic regions. Such organisms may acquire a far more profound understanding of astronomical cycles than humans over cosmic timescales. Their genetic material or behavioral patterns may contain information about galactic dynamics, stellar evolution, and the long-term changes in the environment of our solar system, making them living libraries of cosmic history. The most intriguing possibility for our alternate Earth, however, is that intelligence might eventually appear, albeit in a form so dissimilar from our own that we might not recognize it as consciousness right away. The subterranean microbial networks on the planet may eventually develop a level of collective intelligence that enables them to reflect on the nature of the universe and their own existence. Consciousness may be experienced by such a planetary mind in ways that transcend both global space and geological time. Its ideas could develop over millions of years, encoded in the gradual chemical alterations of ecosystems at the continental scale. The mineral structures of old rock formations may contain its memories, forming a kind of geological consciousness that retains knowledge of the planet's whole past. Eventually, this planetary intelligence may be able to perceive the universe outside of its own planet, detecting the gravitational pull of other planets, the shifting cosmic radiation intensity as the solar system passes through the galaxy, or even the minute impacts of far-off stellar explosions on the chemistry of its planet. Instead of the external observation that defines human science, it might create a science based on first-hand experience of cosmic forces. Individual minds like ours may have very different values and concerns than such a being. It may be more concerned with planetary stability and cosmic harmony than we are with our own personal survival and happiness. The orchestration of global chemical cycles and the creation of stunning mineral formations that span continents are two examples of how creativity can be expressed in literature and art. This planetary consciousness may eventually even discover methods to connect with the universe outside of its own world. It might be able to produce detectable signals by altering the magnetic field or atmospheric composition of its planet. It could use controlled variations in the planet's interaction with the solar wind or subtle changes in the planet's infrared signature to convey messages. A network of planetary minds exchanging information across interstellar distances could be formed if such intelligences were present throughout the universe. As patient and tenacious as the geological processes that gave rise to their consciousness, their communications may develop over millions of years. Their conversations, which are invisible to our instruments, but rich in meaning for minds that think in cosmic timescales, may be about the nature of existence and the meaning of the universe at this very moment. As we get ready to wrap up our exploration of this alternate history, let us pause to consider the incredible series of events that brought us into this world. The right planet size to sustain liquid metal in its core, the right rate of cooling to establish convection currents, and the right rotation rate to produce the Coriolis effects required for field generation, all played a complex role in the development of Earth's magnetic field. Our world might have gone in the direction we've been envisioning tonight if any of these elements had been substantially different. Rather, by what appears to be a remarkable cosmic accident, our planet created and preserved the magnetic shield that allowed us to exist. Because of this protection, our atmosphere was able to stabilize and thicken. It created the conditions for photosynthesis to develop and change the chemistry of our planet. Over billions of years, it established the stable conditions necessary for complex life to develop, eventually giving rise to consciousness and intelligence. With its astounding diversity of ecosystems and life forms, it enabled the rich biosphere that envelops us today. Maybe you'll become more conscious of the unseen forces that guard and surround you as you fall asleep tonight. The magnetic field that envelops our planet like an unseen hug is responsible for everything, from the air you breathe to the steady temperature that keeps you comfortable to the shielding from cosmic radiation that keeps your cells functioning normally. Though it is based on actual science and real possibilities, our voyage through the alternate Earth has been a thought experiment. Mars serves as a reminder that planets can lose a large portion of their atmosphere and their magnetic shield. What can occur when atmospheric conditions drastically change over planetary timescales is demonstrated by Venus. In its stable, magnetically shielded state, Earth may be more unique and valuable than we frequently think. However, this story also contains wonder and hope. We have learned that life is extraordinarily inventive and persistent. Biology manages to adapt and flourish even under the most trying circumstances. There may be life forms in the universe that exist under circumstances we think are unthinkable, intelligence that arises through unimagined channels, and consciousness that perceives the world in ways that are entirely different from our own. We get hints of what might be possible elsewhere in the universe, from the extremophile organisms that flourish in the harshest conditions on Earth. Rich biological communities can arise without the need for sunlight, as demonstrated by the intricate ecosystems that surround deep-sea hydrothermal vents. The universe may be far more alive than our earthly perspective occasionally permits us to imagine, given the extraordinary adaptability and inventiveness of life on our own planet. One of the universe's most amazing accomplishments may be our own consciousness, our capacity to reflect on these issues and envision different planet histories. This chain of emergence, matter organizing into atoms, atoms into molecules, molecules into cells, cells into organisms, and organisms into beings with the ability to question their own existence, may be extremely uncommon in the cosmic context, or it may be more frequent than we think, simply taking on forms we haven't yet learned to identify. We are also reminded of the significance of the systems we frequently take for granted by the tale of our alternate Earth. Changes that appear minor in geological time, but significant in human experience, have the potential to upset processes that appear so stable and dependable, such as climate stability, atmospheric protection, and the cycling of elements between the atmosphere, oceans, and land. The tale of what Earth might have been without its magnetic field serves as a reminder of how valuable our current circumstances are, especially in light of the problems we face today with climate change and environmental disruption. Even though we can't control the magnetic field of our planet, we can still affect a lot of the other systems that keep our planet habitable. The kind of world we leave for future generations will depend on the decisions we make regarding conservation, technology, energy use, and land use. Our alternate Earth story teaches us that habitability is not a given because it depends on the intricate relationships between numerous systems, some of which are out of our control, but others of which are greatly impacted by human activity. Most significantly, our journey tonight serves as a reminder of the importance of imagination and curiosity in comprehending our place in the cosmos. We can investigate not only what is, but also what might have been and what might be thanks to science. We can better understand the forces that continue to shape our world and develop a greater appreciation for the path that led to our existence by imagining different histories for our planet. We will learn more about not only our own world, but also the possibility of life elsewhere in the universe by investigating the questions we have discussed tonight, such as the conditions necessary for life, the evolution of intelligence, and the interactions between planetary systems. We will be searching for the clues that tell us whether those far-off worlds have the kinds of defense mechanisms that allowed life on Earth to exist as we improve telescopes and more advanced methods for researching planets around other stars. Perhaps you can find solace in the soft, imperceptible embrace of our planet's magnetic field as you get ready for bed tonight. It had existed for a very long time before life appeared, and hopefully it will still provide refuge and protection for our planet long after human civilization has assimilated into its prehistoric past. There is a sort of cosmic tenderness in its silent, continuous work, the universe tending to itself, establishing safe havens where beauty and consciousness can blossom. Good night, and I hope you awaken tomorrow feeling even more awed by the unseen protectors who enable your life. We are all safely transported through the cosmic night toward whatever mornings lie ahead as the Earth continues to spin through space, encased in its magnetic cocoon. The magnetic field of our planet is a symbol of something valuable in a universe that can appear vast, cold, and uncaring. Stability, protection, and the patient maintenance of the conditions necessary for the existence of life, love, and consciousness. Take comfort in the fact that you're a part of a remarkable story, a story of planetary evolution and cosmic forces that brought you to this moment of awareness and wonder despite seemingly insurmountable odds. You live on a planet that has sustained life for billions of years, are composed of star stuff, are shielded by invisible fields, and are warmed by a nearby star. That is no small miracle in the vastness of the universe. I hope you'll keep learning about the amazing tale of our planet and its place in the universe, if this voyage through time and space has piqued your interest. Numerous opportunities exist for us to view the world from a different perspective and recognize the extraordinary nature of things we frequently take for granted thanks to science. Rest in peace, knowing that you are protected by forces you cannot see, but that are always looking out for you. Until we cross paths again in another investigation of the mysteries of the cosmos. Good night, fellow time and space travelers. Rest easy under the watchful eye of Earth's unseen protector, and awaken the next day with a fresh understanding of the cosmic synchronicity that allows you to be here. Not only is the magnetic field that envelops our planet a physical phenomenon, but it also serves as a reminder that within this vast universe, there are forces committed to maintaining the conditions necessary for wonder and consciousness to thrive. Imagine our planet spinning tonight, its familiar continents strewn across the blue ocean like jigsaw pieces. Australia floats in glorious isolation. Africa is tucked away against the Atlantic. Europe is there, and North America is here. Doesn't this geography seem as permanent as the stars themselves? But in reality, what we're seeing is only a single frame in the longest movie ever produced. About 300 million years ago, long before the first dinosaur made its mark in prehistoric mud, the story of Pangaea began. Imagine Earth as a young planet that is still figuring out how to organize itself. The continents were not the dependable, stable formations that we are familiar with today. They were restless nomads, driven and drawn by forces that existed far below the surface. All of Earth's land masses progressively merged during this period, resembling the pieces of a huge, three-dimensional puzzle. They created what geologists would later refer to as Pangaea, which is derived from Greek words meaning all Earth. This was not merely a bigger version of any continent that exists today. Pangaea, a single enormous landmass encircled by the vast ocean known as Panthalassa, was something completely different. Picture yourself standing on this supercontinent's shore. The land behind you extends for thousands of miles in all directions. Reaching the other side of the world doesn't require island hopping or ocean voyages. It was just solid ground that connected Siberia to South Africa and what is now Morocco to Manhattan. When you consider that a large portion of Pangaea's interior was located more than 1,000 miles from the closest ocean, the idea of being landlocked itself takes on a new significance. This landmass's size defies our current knowledge of geography. It could take months to see the sea if you started walking toward it from the center of Pangaea. Nowhere on Earth today would have been as cut off from the sea as the interior regions would have been. In contrast to the deep interior of our hypothetical persistent Pangaea, even the centre of Australia or Siberia appears to be coastal. However, Pangaea did not survive in our timeline. Eventually, it started to fall apart due to the same restless forces that had held it together. The gradual disintegration of the supercontinent started around 200 million years ago. Initially, it divided into two smaller supercontinents, Gondwana in the south and Laurasia in the north. Then these also started to break apart, sending the fragments to their present locations around the world in slow rotation. Tens of millions of years passed during this breakup, which is longer than complex life has existed on land. Species changed and vanished, mountains rose and fell, and the continents persisted in their patient dance. The Americas were divided from Europe and Africa by the Atlantic Ocean, which opened like a flower that blooms slowly. After breaking away from Antarctica, India started its incredible journey northward, eventually colliding with Asia to form the Himalayas. The magnitude of the forces causing this continental drift is almost poetic. Like a pot of thick soup cooking on a cosmic stove, the Earth's mantle churns deep beneath our feet. The vast circulation patterns created by hot material rising from close to the core, spreading outward, cooling, and sinking back down, dwarf any surface weather system. The continents are pulled along by these convection currents, like leaves on a sluggish stream. Let's imagine a different story, though, tonight. What if the deep forces that propel continental drift had operated in a different way? Maybe a more stable pattern had developed among the convection currents in the Earth's mantle. Perhaps a more balanced system that held all the continents in place had been created by the more evenly distributed heat flow from the planet's core. Regardless of the process, suppose that Pangaea had just remained together after it was formed. What sort of world would that have produced? The weather is the first thing we would notice, and this is where our made-up world starts to feel very different. The arrangement of continents and oceans has a significant impact on our current climate. London is warmer than cities much further south due to the Gulf Stream, which transports warm water from the Caribbean to Western Europe. England might have a more Labrador climate if this current didn't exist. The unique configuration of land and sea, the way the Himalayas direct air currents, and the temperature differential between the Asian landmass and the surrounding oceans are all factors that contribute to the monsoons that provide billions of people in Asia with life-giving rain. This would all be different on Pangaea. The interior of the supercontinent would have some of the most severe continental climate conditions ever observed on Earth, since there would be no Atlantic Ocean to regulate temperatures or Pacific currents to disperse heat globally. The extremes of the seasonal temperature fluctuations would be stunning. Death Valley would seem pleasantly cool in comparison to the frequently scorching summers in the centre of Pangaea. We're talking about temperatures that could reach 140 or even 150 degrees Fahrenheit inland, and they could last for months at a time over large areas. The opposite extreme would arrive during the winter. Temperatures in the interior of Pangaea might drop to -80 or -100 degrees Fahrenheit if the surrounding oceans didn't act as a moderating influence. These are protracted cold seasons rather than short-lived cold snaps, which would render the interior areas uninhabitable for months at a time. Since entire ecosystems would have to move thousands of miles between summer and winter ranges, the seasonal migration patterns would be completely different from what we observe today. The most livable places would be along the coast, which is fortunate to have the ocean's moderating effect. Conditions may be mild and stable here, where the shores of Pangaea meet the vast Panthalassa Ocean. Every mile you travelled inland, however, would take you farther away from that oceanic influence and into a land of extremes that would test life in ways we can hardly fathom. Think about how the rain would behave in such a world. Nowadays, a large portion of our precipitation originates from water that has evaporated from the oceans and been transported inland by wind patterns. Very little moisture would be able to reach the deep interior regions of Pangaea due to their great distance from the ocean. It's possible that the supercontinent's center is a desert that, in contrast to the Sahara, is a vast expanse of sand and rock that stretches for thousands of miles in all directions. Ironically, though, the weather events would be disastrous if moisture did make it to these interior regions. Consider storm systems that form over the ocean and then move thousands of miles inland without running into any major obstacles. These storms would have the time and room to develop into weather phenomena that are much larger than anything we have seen before. Supercells the size of entire nations could form from thunderstorms, producing tornadoes that could continue to be powerful for hundreds of miles. Over such a large landmass, the seasonal winds would produce their own spectacular phenomena. During the summer, Pangaea's interior heated, creating massive low-pressure systems that drew air in from the coasts. Dust and sand from the interior deserts could be carried thousands of miles by these winds, which could reach speeds that would be considered permanent hurricanes. From space, one could see the dust storms, massive brown clouds that could cover regions the size of contemporary countries. I sincerely hope you will think about subscribing to follow me on my future explorations if you are enjoying this voyage into a different Earth. These thought experiments have a profoundly fulfilling quality, don't they? They give us a new perspective on our own world. Let's now take a moment to imagine what the actual landscape might look like. The geography of Pangaea would be completely foreign to us without the distinct mountain ranges and river systems that developed as the continents broke apart and collided in novel ways, as well as the erosion patterns produced by our current configuration of distinct continents. Consider the formation of mountains on our planet. The collision of continents produced many of our great ranges. When India slammed into Asia, the Himalayas rose. During Pangaea's initial assembly, North America and Africa collided to form the Appalachians. Africa and Europe collided to form the Alps. These collision-based mountain ranges would not have developed in our alternate universe, in which Pangaea never broke apart. Rather, it would be a different force that would drive the mountain building on our persistent Pangaea. Massive shield volcanoes, possibly bigger than anything we see today, could be formed by volcanic activity. We can see what happens when volcanic hotspots have time to develop without being swept away by plate tectonics in the Hawaiian Islands. Such hotspots could produce volcanic peaks that dwarf Mount Everest and produce truly astounding mountains on stable Pangaea. The Appalachian Mountains would have had hundreds of millions more years to develop. In our world, they were created when North America and Africa collided during Pangaea's assembly. If the Atlantic Ocean hadn't opened up to separate the continents, these mountains might have kept growing, or they might have been eroded into soft, undulating hills. They would not resemble the Appalachians of today in any way, though the precise result would depend on the tectonic activity that is still occurring beneath them. On our alternate Earth, rivers, those patient landscape sculptors, would take completely different routes. Water from the Andes is now transported across the continent to the sea by the Amazon, that powerful conduit of South America, which flows eastward to the Atlantic. The Amazon might flow completely differently on Pangaea if its waters weren't received by the Atlantic. It might eventually reach the supercontinent's northern shores after bending northward through what are now Colombia and Venezuela. Or perhaps it would be a part of a vast network of rivers that swept westward across Pangaea's whole width, merging with waters from Africa and Asia to form an unthinkable transcontinental waterway. Consider a river that rises in the mountains of what we call Tibet, travels through the plains of what we call Europe, gathers tributaries from what we call Africa, and ends up at the sea close to what we call Peru. A river like that would span thousands of miles, traverse various climate zones, and transport sediments from a variety of geological formations. The resources and trade opportunities available to the civilizations that grew up along such a waterway would be unmatched in our world. The Nile, a comparatively small river in our world that traverses a slender strip of green in the African desert, may be a component of a much larger system on Pangaea. The Nile might merge with other African rivers to form a vast inland sea or flow all the way across the supercontinent to reach the ocean on the other side if the Mediterranean and Red Seas didn't restrict African drainage patterns. Currently flowing south through North America to the Gulf of Mexico, the Mississippi could instead flow eastward across the connected landmass, joining rivers from Asia and Europe to form previously unheard-of continental drainage systems. Building cities and civilizations alongside such rivers would present enormous engineering challenges, but it would also present opportunities for trade and transportation. On Pangaea, lakes would also convey a different message: the unique glacial history of North America, which was influenced by ice sheets that formed and melted as the continent drifted to its current location, is partially responsible for the existence of the Great Lakes. Glacier patterns would be entirely different on our stable Pangaea, possibly resulting in inland seas that are much larger than anything we currently know. Imagine a Mediterranean-sized freshwater sea in the centre of the supercontinent that is nourished by rivers coming from all sides. In this context, the story of ice ages becomes especially intriguing. The location of continents in relation to the poles, the configuration of ocean currents, and the particular processes by which ice sheets can form and spread all affect ice ages on our planet. Ice ages on Pangaea would follow completely different laws. The massive landmass may sustain ice sheets of previously unheard-of magnitude during glacial periods. Glaciers could stretch thousands of miles from the polar regions toward the equator during an ice age on Pangaea, forming ice sheets that would cover an area larger than present-day Antarctica. The land beneath such ice masses would be depressed by their weight, forming massive basins that could eventually fill with meltwater during interglacial periods. A Pangaean ice age ending would be an unthinkable spectacle. Biblical deluges would seem like spring showers as the enormous ice sheets melted and unleashed floods. Meltwater rivers could sculpt canyons throughout the supercontinent, producing topography that would dwarf the Grand Canyon. With each glacial cycle, the rushing water would carry massive loads of sediment, possibly filling inland seas and forming new landscapes. Let's now focus on life itself, as this is where our alternate Pangaea diverges from the real world in the most fascinating ways. Isolation is essential to evolution. Animal and plant populations gradually diverge into separate species as a result of adaptation to their unique environments. A prime example are the finches of the Galapagos Islands, which served as a source of inspiration for Darwin's theories on natural selection. The variety that provided such a clear picture of evolution in action was the result of the slightly different ways that each island's distinct environment shaped its finch population. Such isolation would be far less common on our Pangaea, which never broke apart. With the exception of climatic zones and physical obstacles like mountain ranges and rivers, species may be able to spread throughout the entire supercontinent. This could have led to completely different evolutionary pathways that are hard for us to imagine, but it could also have prevented much of the amazing diversity that we see in life today. Think about the warm-blooded animals that would eventually become our own species, the mammals. Different groups of early mammals were isolated on different continents in our world due to the breakup of Pangaea. This resulted in the evolution of placental mammals in most other places, marsupials in Australia, and the now extinct multituberculates in other places. The diversity of mammals that exist today is the result of the distinct evolutionary paths taken by each group. The competition between these groups would have been very different on our Pangaea, which was never divided. A world where all mammals use similar reproductive techniques might have resulted from one group controlling the entire supercontinent. Suppose that all mammals were marsupials and that they carried their young in pouches. Or suppose that the placental strategy was so effective that marsupials never had a chance to establish themselves anywhere. On the other hand, even more dramatic mammalian evolution could have resulted from Pangaea's enormous size and diverse climate. Mammals may have evolved into forms that are nearly alien to us due to the vast distances and drastic climate gradients they had to adapt to. Mammals that have adapted to the intense heat of the interior deserts might be able to withstand temperatures that would kill any mammal in the modern era, or cold-adapted species that could survive the harsh continental interior winters, growing layers of fat and fur that would make Arctic animals appear tropical in comparison. Large predators make for an especially interesting story. Each continent in our world has its own apex predators. North America developed its own distinct lineages, Asia produced tigers, South America produced jaguars, and Africa gave us lions and leopards. These large cats each reflect millions of years of evolution in relative isolation, adjusting to the unique hunting conditions and prey animals of their respective continents. These various cat lineages may never have split apart on Pangaea. We might have a single, extremely successful predator species that spreads throughout the entire supercontinent in place of the stunning diversity of big cats that we see today. This uber cat, which evolved to hunt the enormous prey animals that might develop on such a vast landmass, may be bigger and more powerful than any contemporary big cat. Or it's possible that a completely different kind of predator won the competition. Perhaps the dominant predators on Pangaea were large birds, like the terror birds that once dominated South America. Imagine small dinosaur-sized raptors that hunt in packs across the supercontinent's vast plains. They would be flightless, but incredibly quick. The story of the herbivores would also be different. Different continents in our world have come up with different ways to deal with the problem of eating a lot of plants. Australia produced giant wombats and kangaroos. South America produced ground sloths and glyptodonts, and Africa produced elephants and rhinos. The evolution of herbivores that dwarf anything in the modern world and are suited to travelling great distances between seasonal feeding grounds may be observed on Pangaea. Imagine herds of plant eaters the size of small buildings, moving thousands of miles between the interior plains, where they feed during the short, scorching summers, and the coastal regions where they spend the winter. These animals may have developed unique adaptations to survive Pangaea's harsh climates, such as the capacity to estivate during the hottest times of the year, or the development of thick fur that they could shed entirely during summer migrations. Another interesting case study is birds. On remote continents or islands, many of our most amazing bird species developed. The remarkable diversity of South American hummingbirds, Australia's varied parrots, and New Zealand's distinctive birds, all of which evolved without mammalian predators, all developed in relative isolation. It's possible that bird evolution on Pangaea followed more consistent patterns, which might have resulted in less diversity, but also some incredibly amazing adaptations. Pangaea might have pushed bird evolution toward better flight abilities if it hadn't been for the isolation that allowed flightless birds to evolve on islands and continents free of predators. We may witness species that have evolved to live permanently in the air, landing only to nest, or birds that are capable of truly epic migrations, traversing the entire supercontinent on a seasonal basis. On the other hand, birds with exceptional temperature tolerance may have evolved as a result of Pangaea's harsh climate. Maybe we would see birds that could withstand the harsh winters of the continental interior, or species that could fly over the blazing interior deserts during the hottest part of the day. On Pangaea, the evolution of flight itself may have gone in a different direction. There would be intense evolutionary pressure for effective long-distance flight because of the enormous distances to cover. With the help of specialized metabolisms and flight adaptations, birds may have developed flight abilities that far surpass what we see today, possibly enabling them to fly for weeks at a time without landing. What about the evolution of humans? Of all the possibilities, this one presents some of the most fascinating. According to our timeline, early humans first evolved in Africa before migrating in waves around the globe and coming into contact with diverse environments that influenced them in different ways. A tale of extraordinary adaptability and diversification can be found in the evolution of various human populations that have adapted to everything, from tropical forests to Arctic conditions. Different genetic adaptations developed as a result of human populations being isolated on different continents for tens of thousands of years. Some populations' capacity to digest milk into adulthood, the Andean and Tibetan peoples' adaptations to high-altitude living, and the different skin pigmentation adaptations to varying levels of solar radiation are all examples of evolutionary responses to distinct environmental challenges faced separately. Human evolution may have been more homogeneous on Pangaea, but it may also have been sped up by the ongoing interactions between various groups. Human populations would have been in constant contact throughout the supercontinent, rather than evolving in relative isolation for thousands of years. A more genetically homogeneous human species may have resulted from this continuous gene flow, which may have inhibited the emergence of unique local adaptations. On the other hand, Pangaea's harsh environment may have pushed human evolution in unimaginable directions. Human adaptations may have been far more extreme than those observed in contemporary populations due to the difficulty of surviving in the sweltering interior during the summer and the bitter cold during the winter. Maybe we'll see people who can withstand temperatures that would kill any modern person in a heartbeat. Without a doubt, the course of human technological development would have been different. The necessity of overcoming water barriers and surviving in isolation has fueled a large portion of our technological advancement. These stresses would not exist on Pangaea, but they would be replaced by the necessity of surviving in harsh continental environments and making long overland treks. Early humans on Pangaea may have directed their technological innovation toward long-distance overland travel and desert survival rather than boats and ships. Advanced techniques for navigating across large, featureless landscapes, specialized equipment for surviving extreme temperatures, and sophisticated water-finding and water-carrying technologies could all be developed. Another intriguing conjecture is language development. Thousands of different languages have developed in our world as a result of human populations becoming separated. Languages spoken by remote communities, such as those in the Amazon region or Papua New Guinea, frequently have distinctive grammatical structures and ways of structuring ideas that reflect various worldviews. Because human groups on Pangaea were constantly in contact with one another, we might have witnessed the emergence of a more cohesive language throughout the supercontinent, or even more intricate linguistic evolution, as various groups continued to communicate while adjusting to the various climatic zones spread out across the enormous land mass. Although there is constant borrowing and influence between the languages of desert dwellers, mountain peoples, and coastal populations, the linguistic diversity may be arranged along climatic rather than geographical lines. The necessity of communicating over great distances may have sped up the development of writing systems. Writing may have become a continental necessity much earlier in human history, leading to more advanced and standardized writing systems, rather than evolving slowly in isolated areas. I'd love to know if this exploration is as thought-provoking to you as I hope it is. If you're enjoying these bedtime excursions through alternate histories and possibilities, please consider subscribing. Thinking about these alternative routes our world could have taken has a certain enchantment. In this scenario, agricultural development assumes new dimensions. The Fertile Crescent, China, Mesoamerica, the Andes, and New Guinea are just a few of the places in our world where agriculture was independently invented multiple times. Different crops and animals were domesticated in each region according to local conditions. Middle Eastern wheat and barley, Asian rice, American corn and beans, and South American potatoes. A wide variety of agricultural systems, each tailored to particular climates and conditions, resulted from this autonomous development. When it eventually happened, crop exchange between regions transformed agriculture and allowed for population growth that would not have been possible otherwise. For example, New World crops like corn and potatoes were brought to Europe and Asia, which helped to fuel enormous population growth. Agricultural innovations would have proliferated across the interconnected landmass on Pangaea far more quickly. When wheat was domesticated in one area, it could swiftly spread to other areas thousands of miles away with similar climates. Since advancements in plant and animal breeding would have been dispersed throughout the supercontinent, this could have resulted in a faster rate of agricultural development overall. But it's also possible that this quick spread increased human society's susceptibility to agricultural catastrophes that affect the entire continent. In our world, food can frequently be imported from other regions with different climate patterns when crop failures occur in one area. Climate events could impact much larger areas at the same time on Pangaea. Large areas of the supercontinent might experience crop failures due to a volcanic eruption that cooled the climate globally, which could result in famines of a never-before-seen magnitude. It's also possible that the crops that took over were quite different. Pangaea may have created a more homogeneous agricultural system based on the plants and animals most adapted to the harsh continental climate, rather than the regional specialization we observe today. The staple crops may be plants that can withstand both hot summers and harsh winters, creating agricultural systems that are very different from what we have today. It's also possible that the relationship between domestic and wild plants will develop differently. Domesticated crops are frequently separated from their wild relatives on our fragmented planet, resulting in genetic bottlenecks that occasionally expose our food crops to pests and diseases. Domesticated plants may sustain continuous gene flow with wild populations on Pangaea where landmass connections are continuous, potentially resulting in more resilient agricultural systems. The patterns of animal domestication would be completely different. On Pangaea, the well-known Jared Diamond explanation of why some animals are domesticable while others are not may require a thorough revision. Given that all wild animals could be found anywhere on Earth, humans may have had access to a far greater variety of potential domesticated animals, or may have domesticated well-known animals at an earlier stage of their evolution. What if early Eurasian farmers had had access to American llamas and alpacas, which would have served as pack animals and sources of fiber in areas where sheep and cattle were scarce? Imagine that thousands of years before our time, early Chinese civilizations had access to African elephants, which could have revolutionized construction and agriculture. Think about the effects of having kangaroos and other Australian animals available for domestication throughout the supercontinent. The evolution of Native American civilizations was significantly impacted by the Americas' lack of horses in our timeline. Since horses would have been available everywhere on Pangaea, cavalry and mounted warfare might have developed more uniformly throughout all human societies. In our timeline, this could have avoided the striking military advantages that gave some civilizations the ability to subjugate others. It would radically alter the history of human migration and settlement patterns. Human expansion on Pangaea would have been a slow overland process rather than the great oceanic voyages that brought people to the Americas, the Pacific Islands, and Australia. It's possible that Polynesian peoples would never have developed the excellent navigational abilities that enabled them to traverse large oceanic regions using only conventional wayfinding methods. Humans may have evolved navigational skills to traverse huge deserts and mountain ranges rather than the open ocean, becoming experts at surviving in the supercontinent's harsh interior climates. This alternative expansion pattern would have significant psychological and cultural effects. It took a great deal of bravery and ingenuity for people to cross the oceans and reach new continents in our world. Many cultures developed myths based on these expeditions, telling tales of courageous forebears who sailed into the unknown to discover new territories. The foundational stories on Pangaea might tell of ancestors who crossed the bitter mountain passes or stepped into the blazing interior, but the essence of these tales would be very different. The patterns of cities and trade routes would be completely different. Many of the world's greatest cities have grown up around natural harbours or where sea routes converged with land routes. The historical significance of Venice, Constantinople, London, and New York can be partially attributed to their advantageous locations in relation to water transportation. The most significant cities on Pangaea may have been those situated at the intersections of various climate zones or along the major rivers that cut through the interior. Consider the capital of a massive Pangaean empire. It may be situated at the centre of the supercontinent, equally spaced from every region, as opposed to on a coast like so many of the great cities of our world. With temperature fluctuations that would test any urban planning, such a city would have to contend with the formidable challenge of an extreme continental climate. The city may be a nomadic capital that alternated seasonally between various climate zones, or it may have to be mostly underground during the harsh seasons. Such cities would require extraordinary engineering. Structures would have to endure temperature fluctuations that are greater than anything we have ever encountered. It's possible that the architecture will evolve in entirely different directions, focusing more on underground construction and thermal mass than on the aesthetic factors that have influenced architecture in our more temperate climates. A major problem for any inland city on Pangaea would be the supply of water. Interior Pangaean cities may need to create complex systems for gathering and preserving water, in contrast to coastal cities that can rely on desalination or adjacent rivers supplied by ocean evaporation. Perhaps massive cistern systems, hundreds of miles of subterranean aqueducts, or groundbreaking water recycling technologies that surpass current standards would be developed. Since trade routes would have to be overland, transportation technologies that could withstand harsh conditions would have to be developed. The great vessels of commerce may be specialized overland vehicles that can traverse the interior's bitter mountain passes and scorching deserts in place of ships. These could be massive wheeled vehicles pulled by groups of animals with special adaptations, or they could be the earliest examples of steam-powered or even solar-powered transportation for traversing the sun-drenched interior regions. Additionally, there would be fundamental differences in the relationships between various civilizations. Before coming into contact with one another, civilizations in our world frequently evolved independently for centuries or even millennia. A large portion of world history was shaped by the dramatic meetings between formerly isolated civilizations, such as the meeting of Europeans and Americans. Our world has been significantly shaped by the technological advantages that certain civilizations have developed in isolation, the diseases that spread when previously isolated populations come into contact, and the cultural exchange that takes place during these encounters. Because overland contact would always be a possibility on Pangaea, diseases, cultural practices, and technological advancements would spread much more slowly but steadily. As nearby societies fought for resources across the vast landmass, this could have resulted in more ongoing, lower-level conflict, but it could also have avoided the stark technological differences that defined our world's history of civilizational contact. No civilization could emerge in total isolation if there were no ocean barriers. Eventually, traders, migrants, or conquerors from other areas would come into contact with even the most isolated groups. Since innovations would have spread swiftly throughout the entire supercontinent, this could have resulted in a faster overall rate of technological and cultural development. The development of the distinctive cultural and technological solutions that emerged from isolation in our world, however, may have also been impeded. On Pangaea, disease patterns would be entirely different. Isolated populations in our world have frequently become immune to diseases that are specific to their area, but they are still susceptible to diseases that are specific to other areas. The consequences of prolonged geographic isolation are reflected in the devastating effects of European diseases on Native American populations. The spread of plague along trade routes and the regional variations in disease resistance that influenced colonial encounters. Diseases would spread more easily throughout the entire landmass on Pangaea due to the constant contact between populations, but populations would also have more opportunities to build up broader resistance. As populations adapted to a greater variety of pathogens over longer periods of time, this could have resulted in either more catastrophic pandemics that could have afflicted the entire human population at once or, on the other hand, more robust overall human health. The continuous knowledge sharing among healers from various areas may have sped up the development of medicine, but it may also have faced the difficulty of addressing increasingly complex disease environments where pathogens from different parts of a supercontinent could interact in unpredictable ways. In this context, the term exploration itself assumes a different meaning. Pangaean exploration might concentrate on entering the hostile interior regions of the supercontinent rather than an era of exploration motivated by the desire to discover sea routes to far-off places. By discovering passes through mountain ranges that connected various climate zones, or by charting river routes through the centre of the landmass, the great explorers may have learned to survive in the harsh continental climates. Compared to ocean voyages, these interior expeditions may be even more difficult. Interior exploration on Pangaea would require survival skills tailored to the most harsh terrestrial conditions on Earth, whereas ocean crossing required navigational skill and bravery. Without the celestial reference points that allowed ocean navigation, explorers would have to endure temperature extremes that are greater than anything we experience on Earth, carry massive amounts of water across desert regions, and navigate over great distances. Compared to the maps of our era of exploration, the maps produced by such expeditions would depict stories of discovery that are very different. Rather than mapping new continents and ocean routes, Pangaean cartographers might map mineral resources dispersed throughout the vast landmass, seasonal animal and nomadic migration routes, and water sources across vast deserts. Pangaea would be affected very differently by both natural and man-made climate change. Climate change-threatened species in our world frequently have the choice to migrate to more hospitable habitats, sometimes even across oceans to continents. Overland migration would be simpler on Pangaea in certain respects, but it might be more challenging in others due to the supercontinent's immense size and stark climate variations. During a period of climate change, a species that is acclimated to Pangaea's mild coastal regions may not be able to traverse the harsh interior to reach other suitable coastal areas. During climate change, the interior areas may serve as a massive barrier, keeping coastal species from getting to other coastal refugia. On the other hand, species that have adapted to the harsh interior conditions may have access to vast ranges, which could make them more resilient to changes in the climate, but also highly dominant when the circumstances are right. Human societies would encounter comparable difficulties. If moving to another coastal area meant traversing thousands of miles of hostile interior territory, a coastal civilization threatened by rising sea levels or shifting weather patterns might find it very challenging. Since migration would not always be a practical option, this could result in the development of more robust adaptation strategies. Additionally, the scope of climate impacts may be more severe. The existence of several continents and oceans helps to moderate and disperse the effects of volcanic eruptions, which can have regional or even global climate effects. Major volcanic eruptions may have more severe and protracted effects on Pangaea because of the massive landmass, which may produce more extreme seasonal temperature swings and more persistent weather patterns. The effects of an ice age would be especially striking. The massive landmass could sustain ice sheets of previously unheard of proportions during glacial periods, possibly enclosing regions bigger than present-day Greenland and Antarctica combined. On a scale that is dwarfed by anything in our geological record, the weight of such ice masses would drastically change the continent's shape, forming massive basins and altering river courses. Whole regions would be reshaped by flood events caused by the melting of these ice ages. The volume of water trapped in such enormous ice sheets would be enormous, and its release would result in flooding and changes in sea level that would dwarf current climate change concerns. Human comprehension of the world would also evolve along distinct trajectories. Observations of ships vanishing over the horizon and the various stars visible from various latitudes contributed to our timeline's conclusion that the Earth was round. Humans may have created quite different models of geography and astronomy on Pangaea, where there was no limit to overland travel. Since the majority of human experience involved travelling overland across what seemed to be an endless, flat surface, the idea that the Earth is a sphere may have been more challenging to develop. Alternatively, because observers could travel thousands of miles overland to make observations from drastically different latitudes, the extreme distances possible on Pangaea may have facilitated astronomical observations. In contrast to the celestial navigation that became so crucial in our maritime world, the development of mathematics and navigation may have placed a greater emphasis on surveying and navigation on land. It's possible that Pangaean scholars created complex mathematical tools that we never had to develop in order to measure and map great overland distances. Tonight, as our exploration of this alternate world draws to a close, let's pause to think about the lessons this thought experiment might teach us. Our actual world, with its divided continents and remote populations, has provided us with amazing diversity, but it has also made us extremely vulnerable. When contact did eventually occur, the isolation that fostered the development of unique species and cultures also left them vulnerable. With its ever-present connections, our hypothetical Pangaea may have been more stable in some respects, and less vulnerable to the catastrophic collapses that have characterized our real history, when formerly isolated populations unexpectedly came into contact with novel diseases, technological advancements, or cultural customs. More resilient and adaptive societies may have been produced by the slow, continuous flow of genes, concepts, and inventions. However, it's also possible that our alternate reality was less inventive, less varied, and less able to produce the unexpected breakthroughs that have contributed to the rich and unpredictable history of our real world. On Pangaea, the innovative solutions that arise from isolation, the distinctive adaptations that arise when populations are split apart, and the creative explosion that happens when previously isolated groups suddenly come into contact would all be absent or significantly diminished. Pangaea's climate problems serve as a reminder of how much geography influences life. We can better understand how much our own livable climate depends on the moderating influence of oceans and the particular land-sea arrangements that we often take for granted when we consider the extreme continental conditions in the interior of our hypothetical supercontinent. The pleasant temperatures that the majority of us enjoy are actually extremely uncommon and rely on the specific configuration of the land masses and ocean currents on our planet. Our thought experiment's biological ramifications demonstrate how much of the diversity in modern life is dependent on the isolation that continental drift brought about. Populations were split apart and given the freedom to evolve in different ways, which is why so much of what we find beautiful and fascinating about life on Earth exists. From the distinctive species of the Galapagos to the unique fauna of Madagascar. A world with fewer species overall might have resulted from Pangaea's lack of this isolation, but those species might have been incredibly resilient and adaptive. Pangaean species may have retained greater genetic diversity within each species, making them more resilient to illnesses and environmental changes, had there not been the genetic bottlenecks that frequently occur in isolated populations. However, we may have also lost out on some of the most amazing advances in evolution. The particular difficulties of island life or continental isolation led to the evolution of many of our most fascinating animals and plants. On Pangaea, the intriguing evolutionary tales of island birds losing their ability to fly, isolated populations developing gigantism, and plants developing special chemical defenses in the absence of particular herbivores would all be different or non-existent. Additionally, there would be a significant shift in the way humans interact with other species. Large animals that had evolved independently of humans have frequently gone extinct in our world due to human expansion. Giant marsupials like Diprotodon and Megalania went extinct when humans arrived in Australia. Mammoths, giant ground sloths, saber-toothed cats, and numerous other large species vanished at the same time that humans arrived in the Americas. From the elephant birds of Madagascar to the moa of New Zealand, the pattern is repeated on islands all over the world. Megafauna and humans would have co-evolved over far longer time periods on Pangaea. It's possible that large animals have improved their defenses against human hunting methods, or that humans have, out of need, evolved more environmentally friendly hunting techniques. The evolution of the naive behaviour that made island species so susceptible to human arrival may have been avoided by the constant presence of humans. On the other hand, the large species may have gone extinct even faster due to the concentrated human population on a single landmass. As human populations grew and hunting skills advanced, megafauna might not have had anywhere to go if continents hadn't been divided. Smaller species that could have coexisted more easily with humans might have taken over, leaving a world with relatively few large animals. It's also possible that the evolution of domestication followed distinct trends. Humans may have had a far greater selection of potential domesticated animals if all wild animals were accessible from anywhere on the planet. However, they may have also had to contend with fiercer competition from predators and wild relatives. It's possible that Pangaea lacked the remote valleys and islands that offered early domesticated animals safe havens, which would have complicated the domestication process. Philosophical and religious development may also follow distinct trends. Before spreading to other areas, many of the great religious traditions of the world developed in relative isolation. Before spreading across continents and oceans, Buddhism in India, Christianity in the Eastern Mediterranean, and Islam in the Arabian Peninsula were all localized belief systems. From their inception, religious concepts would be constantly interacting and competing on Pangaea. More syncretic traditions, where various spiritual practices more easily merged, may have resulted from this. Conversely, as various belief systems came into closer contact with one another more regularly, it could have resulted in more severe religious disputes. The evolution of pilgrimage routes and holy sites would be entirely different. It is possible that Pangaean religions evolved around sacred sites that were reachable by believers from all over the supercontinent, rather than isolated holy sites shielded by geography and distance. Large religious hubs and pilgrimage cities that dwarfed anything in our world might have grown as a result, catering to people from all over the huge landmass. When all land is connected, the idea of the sacred homeland or holy land may be completely different. Pangaean religions may have evolved more intricate spatial theologies, perhaps perceiving the divine as manifesting in various ways throughout the entire supercontinent, rather than discrete sacred geographies divided by oceans. The ongoing cultural exchange that defines our fictional world would be reflected in art and cultural advancement. In our era, isolated communities frequently created distinctive traditions in literature, music, art and architecture. The intricate polyphonic singing of Georgia, the gamelan orchestras of Indonesia, and the unique architectural styles that emerged in various regions were all products of cultural isolation that permitted local customs to flourish independently of outside influences. Cultural exchange would occur much more frequently on Pangaea, which could result in a more uniform, global culture or even more complex fusion traditions as various cultural streams continuously came into contact with and impacted one another. This ongoing cultural conversation may be reflected in the great works of art, which take on forms we can hardly fathom. Traditions and musical instruments may evolve in entirely different directions. Pangean music may reflect the blending of influences from all over the landmass, as opposed to the regional specialization we observe today, where various continents developed unique approaches to making music. In ways that never happened in our divided world, we might witness the emergence of musical traditions that combined aspects of what we would identify as African rhythms, Asian scales, European harmonies, and American instrumentation. Pangea's harsh climate would present special challenges for architecture, resulting in building customs that are unmatched in our world. Buildings would have to endure temperature fluctuations that are beyond the capabilities of contemporary architects. This could have resulted in the creation of innovative construction methods, such as mobile architecture that could be moved according to the seasons, or underground cities that could offer shelter during the harsh seasons. We may be entirely unfamiliar with the aesthetic sensibilities that evolved in such an environment. Extreme landscapes and climates may inspire beauty standards that result in art that is either magnificent or unsettling to us, but it is unquestionably different from anything we have seen in the past. Pangea's distinct geography and history would be reflected in literature and storytelling. Pangean literature might tell tales of epic journeys across the vast interior, tales of survival in harsh climates, or tales of the seasonal migrations that might define life on such a continent, rather than odysseys that traverse oceans and visit foreign lands. If all people lived on the same landmass, the idea of the exotic or foreign would be completely different. Pangean literature might concentrate on the mysteries of the deep interior, the myths of what lies at the centre of the vast continent, or the extreme seasonal changes that would dominate life, rather than tales of enigmatic lands across the ocean. On Pangaea, the patterns of economic development would be completely different. Because of their isolation, various parts of our world have developed specializations in particular resources. Because they were concentrated in distinct, geographically controlled areas, the Middle East's oil, South America's copper and lithium, Africa's diamonds and gold, and Australia's iron ore all gained international prominence. Although resources would be dispersed over a single landmass on Pangaea, all populations would have easier access to them. This could have stopped the rise of the resource-based empires that have defined a large portion of the history of our planet. By controlling island territories or sea routes, no one group could control access to a resource, but the absence of ocean barriers may have increased the frequency and severity of resource-related conflicts. Geographical barriers frequently prevented conflicts from spreading throughout our world and gave defeated populations a place to hide. Conflicts could spread over greater areas and involve more people on Pangaea, possibly resulting in warfare of a magnitude never seen in our history. The lack of ocean barriers may have sped up the growth of trade, but the harsh conditions in the interior may have also had an impact. Long-distance trade routes would have to traverse some of the most inhospitable terrain on the planet, necessitating organizational and technological advancements that we never had to create. Imagine trade expeditions transporting goods between coastal civilizations that are separated by the supercontinent's width, traversing thousands of miles of blazing desert. These trips, which call for extensive preparation and a lot of resources, could take months or even years. The goods would have to be extremely valuable in order to justify such costly and risky transportation, which might result in different patterns of luxury trade than those that exist today. Currency and financial system development may also differ. In our world, some cities and countries were able to control trade and establish highly developed financial systems by controlling sea routes. The overland character of all trade on Pangaea may have resulted in distinct commercial strategies, possibly emphasizing resource management and caravan organization more than the maritime banking systems that evolved in our world. Additionally, the idea of national boundaries would be entirely altered. Oceans serve as natural borders in our world, aiding in the delineation of nations and empires. Boundaries would be more disputed and flexible on Pangaea. Large empires may be able to grow due to the great distances, but they may also be challenging to maintain and manage due to the absence of natural barriers. The development of transportation technology would have been entirely different. Pangean civilizations may have created advanced overland transportation systems in place of the ships and navigational methods that enabled humans to traverse oceans. We may witness the development of vehicles that are suited to harsh climates, possibly including the early adoption of mechanized transportation to displace animal-drawn vehicles in the most inhospitable settings. Building roads and other transportation infrastructure across such a wide range of harsh climates would present tremendous engineering challenges. In certain climate zones, roads may need to be constructed according to different standards, taking into account the thermal expansion and contraction that would take place over such wide temperature ranges. There would also be special difficulties in communicating over long overland distances. Pangean civilizations may have created complex overland communication networks in place of the signal systems that evolved for maritime communication. In order to overcome the difficulties of distance, we might witness the early development of mechanical or even electrical communication systems, or the development of relay systems that use fires or mirrors to transmit messages hundreds of miles away. Human populations and various ethnic groups would have radically different relationships. Geographic isolation and environmental adaptation are frequently linked to ethnic differences in our world. Many of the ethnic and cultural differences that exist today are the result of relatively recent contact between previously divided populations. Human populations on Pangaea might be more homogeneous or even more diverse as various groups adapted to different climate zones while still in contact. Given the continuous contact between populations over much longer time periods, we may observe populations that are specialized for life in the coastal regions, the extreme interior, the mountain zones, or the transitional areas between different climates, rather than ethnic groups based on continental origin. It's possible that these populations have evolved more drastic physical and cultural adaptations than anything we observe in our own world. It's possible that people who adapted to living in the sweltering interior developed improved heat tolerance and distinct water-saving strategies. It's possible that those who evolved for the harsh winters improved their resistance to cold and created new social structures that helped them endure the drastic seasonal shifts. People would need to be prepared for life in such a diverse and demanding environment by educational systems. Pangean education may need to prepare students for interaction with diverse populations across the vast landmass and for survival in multiple extreme environments, rather than the more specialized educational systems that evolved in our more moderate and divided world. Natural philosophy and science would also develop in different directions. The unique geography of our planet allowed us to make observations that led to many of our greatest scientific discoveries. Coastal observations provided the basis for our understanding of tides. Studying the patterns of erosion and mountain formation led to the identification of geological processes. The study of continental differences and island species contributed to the advancement of biology. Scientists would have access to different phenomena and pose different queries on Pangaea. Thermodynamics and atmospheric science may have developed earlier as a result of the harsh climate. It's possible that the great distances hastened the advancement of astronomy and optics. The social sciences and anthropology may have developed earlier as a result of the ongoing interactions between populations. The technology transfer narrative would be entirely different. It can take centuries for technological advancements to spread from one continent to another in our world. It took hundreds of years for the stirrup, which originated in Asia, to make its way to Europe. The same pattern applied to gunpowder. Over the course of decades or centuries, innovations such as paper and printing spread along trade routes. Innovations in technology would proliferate far more quickly on Pangaea, which might result in more consistent technological advancement throughout all human societies. As inventions would be honed and enhanced by inventors throughout the supercontinent, this could have sped up technological advancement overall, while also preventing the technological advantages that allowed some civilizations to dominate others in our world. But Pangaea's harsh environment may have also produced special technological difficulties that would spur innovation in previously unconsidered areas. It's possible that the early development of advanced materials science and climate control technologies was prompted by the necessity to survive in environments that can reach temperatures of 150 degrees Fahrenheit in the summer and minus 100 degrees in the winter. Additionally, there would be new opportunities and challenges associated with knowledge preservation. In our world, knowledge that was lost in one place can occasionally be preserved by isolating it from other areas. During the Dark Ages in Europe, a large portion of Greek knowledge was preserved in the Islamic world. Even when comparable advancements in other areas were lost, Chinese innovations persisted. Since inventions and discoveries would have been preserved in several places at once, the continuous contact on Pangaea may have made knowledge more secure overall. However, because there would be fewer isolated repositories to preserve information during significant disruptions, disasters that affect an entire continent could also result in a more catastrophic loss of knowledge. Libraries and educational institutions may also have evolved in different ways. Pangaean scholarship may have focused on organizations that could communicate and work together over great distances rather than the remote monasteries and academies that preserved and advanced knowledge in our world. This could have resulted in the early creation of systems for academic collaboration and long-distance communication. Living in such a world would have a significant psychological impact that would be hard for us to completely comprehend. Living on a world of divided continents, encircled by oceans, shapes our sense of geography, our comprehension of distance and separation, and our conceptions of home and foreign lands. The way that people on Pangaea relate to distance and space would be entirely different. There would be a completely different sense of possibility and connection if you knew that you could theoretically walk to any other location in the inhabited world. The world may feel more interconnected and more overwhelming in its vastness when there are no absolute barriers like oceans. Seasonal variations would produce life rhythms that are unlike anything we have ever experienced. It may be necessary for entire civilizations to adjust to drastic seasonal shifts, possibly leading to the development of nomadic lifestyles that followed resource availability and temperature over hundreds or thousands of miles annually. In the interior, where most human activity followed seasonal patterns that capitalized on the fleeting moments when extreme conditions subsided, the idea of permanent settlement may be less prevalent. More advanced portable technologies and social structures that were suited to continual mobility may have resulted from this. It's worthwhile to consider what this thought experiment tells us about our own world as we draw to a close our journey through this alternate Earth. Because of the fragmentation of Pangaea and the subsequent drift of continents, the planet we currently live on has conditions that appear nearly impossible for the emergence of complex life and human civilization. A world where life could flourish in remarkable diversity was made possible by the moderate climates made possible by our current land-sea arrangement, the isolation that allowed for the development of diverse species and cultures, and the ocean barriers that offered protection while still permitting eventual contact and exchange. Because of the natural laboratory that our divided continents have provided, life has been able to try out an infinite number of strategies for surviving and procreating. Human exploration and migration eventually brought these divided populations back together, weaving a complex web of genetic, cultural, and technological exchange that has sped up human development in ways that might not have been feasible on a single Pangaea. When compared to the harsh circumstances that might have defined our alternate Pangaea, the mild seasonal variations that most of us encounter, the consistent availability of fresh water, and the stable climate zones that permit predictable agriculture, all of these things that we frequently take for granted are actually pretty amazing. However, our thought experiment also highlights some of the weaknesses in the world we live in today. Vulnerabilities resulted from the isolation that produced such exquisite diversity. When isolated species and cultures eventually came into contact with external influences, they frequently showed signs of fragility. Some of the most traumatic incidents in our history have resulted from the drastic effects of contact between previously isolated populations. Maybe we can learn from this for the future as well. We may be heading closer to the continuous contact that would have defined Pangaea as our world grows more interconnected through technology and international communication. The advantages of this connection are clear: quick innovation sharing, instantaneous communication over long distances, and the capacity to plan responses to global issues. However, we may also be losing some of the advantages of diversity and isolation that influenced our growth. The cultural and biological diversity that has been one of our world's greatest assets may be diminished by the homogenizing effects of global trade and communication. Without the refuge and alternate strategies that geographical separation once offered, the problems we face may increasingly impact all of humanity at once. Perhaps as you get ready for bed tonight, you'll have a dream about traversing that enormous supercontinent and feeling the firm ground beneath your feet that links places that we now consider to be inconceivably far apart. Imagine being thousands of miles from any ocean, in the middle of Pangaea, surrounded by environments that have been shaped by forces and climates that are unlike anything we have ever seen. Imagine the sky being painted in hues we might never see in our world of divided continents and temperate climates as the sun sets over those endless interior plains. Consider the unusual creatures that might have developed there, suited to environments that test life in ways we can hardly fathom. Think about the possible human societies that emerged as a result of the necessity to endure harsh environments while preserving communication over great distances. We live on a planet of amazing diversity and beauty that was formed by the breakup of Pangaea and the ensuing dance of continental drift. The well-known forms of the continents, divided by azure seas, symbolize not only our current location, but also one potential result of profound forces that have shaped our world for hundreds of millions of years. Perhaps your perspective will change when you see a map of the world tomorrow. In the much longer story of our planet's evolution, those continents that appear to be so permanent and distinct are actually only temporary arrangements. Although the world we currently live in is not the only one that could have existed, it is the one that made it possible for us to be here tonight, sharing these stories despite the distances that separate us. A world where a story told in one location can reach listeners in countless others, divided by oceans that once existed and residing on continents that were once joined, was made possible by the breakup of Pangaea. Perhaps the most amazing gift our planet's unique history has given us is this unity, despite diversity, this connection across separation. Rest well, and may your dreams be full of admiration for the amazing world that is, as well as the wonder of all the worlds that could have been.